So first of all, thank you for accepting our invitation. Abhik Giri is currently working in Western Digital, that is SanDisk, Bangalore, as Principal Operations Research Scientist. Abhik is an alumni of BITS Pilani and has been working in the field of operation research for around 13 plus years. So if there is any questions or doubt from the attendees or panelists, you can raise your hand and we will unmute you. So Abhik, you can proceed in the presentation. You can share your screen.
Sure, sure. Thank you so much. Thanks for the introduction and thanks for inviting me to this forum. I hope all of you can see the presentation on the slide, the first slide.
No.
Okay. No. Interesting. Are you able to see the
Yes.
slide now? Okay.
Yes.
Okay. So, okay. So, hi everyone. Welcome to today's session on operations research. So, I think many of you would have operations research as one of your courses in your third year probably. But as a student, we don't know much about the industrial application and how optimization and operations research is used in the real life, in a real world setting. So today's short lecture will, the main aim is to give some idea about the immense applications of operations research in the real world and to motivate you so that at least some of you wish to pursue a career in this field. So as Sir said, we'll have a brief talk of around 45 minutes, and at any point of time, if you have any questions, if you want me to elaborate some point in more details, then please feel free to stop me. So just an introduction about myself. So I am currently working at Western Digital as a principal OR scientist, and I work on different. So Western Digital is a manufacturing company, as you are aware, and we have factories in different parts of the world, and I work on optimization problems related to the factories. And before that, I was working with other organizations like Bayer, Intel, and so on. Yeah. So first, we'll have a quick look at quick introduction of optimization. So optimization is a field within applied mathematics. So there are different terms which are synonymously used: operations research, mathematical optimization, decision support system, and so on, management science. So what do we do in optimization? In optimization, we try to find the best solution of a problem by optimizing. So optimization started as a branch during World War II. So, during World War II, when different countries were trying to find ways to optimize the scarce resources they had, that is when optimization started as a and since the 1940s, there has been a tremendous progress in optimization because the computing power of computers have increased and a lot of algorithms have been discovered, which has made solving large scale industrial problems much easier. So this is how a generic mathematical model look like. There would be an objective function, which would be either a maximization or a minimization function. And in this example, in this slide, I've shown only one objective, but in real world, there could be multiple
Sir,
objectives.
I think your slides are not visible.
Oh, um, you can see the first slide,
Yeah, the
right?
slides are not moving awake. If
Ah,
you keep those in the full screen mode and
Uh-huh.
then toggle between the slides, I think it will roll.
No, it was in full screen mode. 1 second. Okay, so this is the. Are you able to see the first slide now?
it is not in full screen mode actually.
Strange. Share application. Okay. The entire screen. Okay. Okay, now you can see the presentation, right? The first slide.
Yes.
Okay. Okay, 1 second. You are able to see it full screen,
Yes. Yes. Yes, sir.
and you are seeing the next slide now.
Yes, sir.
Okay. Okay. Great. Yeah. Yeah. So probably this is the first slide. So yeah, so this is, I mean, what we already discussed. Yeah, so this is how a generic mathematical model look like. There would be an objective function, which could be a maximization or a minimization, or it could be both. And there could be multiple, in this slide, I have shown only one objective, but in the real world, there could be multiple objectives, each with different priorities. So the objectives could be like maximizing profit, maximizing revenue, or maximizing throughput, maximizing utilization. Or if it is minimization, it could be minimizing cost, minimizing the time required, the number of people required, and so on. And this objective function needs to be maximized or minimized subject to certain business constraints. So the constraints would typically be constraints on resource capacity. So if it is a factory, if you're talking about a factory, then it could be the capacity of the machines, number of people available, number of amount of time that I have, and so on. So and the constraints could be either equal to or lesser than equal to or greater than equal to. So in the optimization problem, in this problem, I need to find the values of the X decision variables. So why do we need optimization? Because as I said, we can maximize or minimize different KPIs. And in a real world, there could be thousands or millions or even more number of possible combinations depending on the problem size, and that is something you cannot do manually. So we'll see why that is so in the next slide. And optimization distributes scarce resources. And in this slide, I've shown some of the resources which could be scarce, and that is what optimization tries to do, how to make the best utilization of these resources. It could be time, money, number of people, equipment, facilities. If it's a vehicle routing problem, it could be number of vehicles, it could be the raw materials. So this slide is more about taking you through the broader picture of analytics. So today we hear a lot about AI, ML, deep learning, machine learning, and so on. So let's look at where optimization falls in that broad chart. So if you look at the graph on the left, this graph shows on the x-axis we have the different types of analysis we can do in any kind of analytical work, and on the y-axis the value the value that is brought about by the analytical work is shown. So as you move from left to right, the most basic analysis you can do around any data is descriptive or diagnostic analysis. So we look at past data and we try to find different patterns from the data. So for example, if it is sales data, we could we could find out what is maximum sales, what is average sales, and so on. So you don't really do any math, you don't really apply any mathematics or statistics on that. You just write some formula and write some code to find some basic patterns from that data. The next step is predictive analytics, where we look at the historical data and we try to uh, based on the historical behavior of something, we try to predict what would happen if for another set of input variables in future. And the last is the prescriptive analytics, which we also call as optimization or simulation. So in prescriptive analytics, we again look at the future and we find out what is the best way to perform some action so that my KPIs are maximized or minimized. So the same thing is demonstrated in the graph in the table on the right. So when we say advanced analytics, we are actually talking about predictive analytics and prescriptive analytics. And the other thing is, as you move along the x-axis from left to right, the difficulty level increases because there would be more mathematical complexity involved, but at the same time, we would be bringing more value to the business. This is something I'll skip. How do you know if you have an optimization problem? So if there is some objective which is to be maximized or minimized, and there are certain restrictions or limitations on the possible values of the decision variables, then it is an optimization problem. So there could be many types of optimization problems. We'll look at some of these in the next slides, but the major ones are supply chain optimization, production planning, and production scheduling. This is mainly in factories. In the financial world, we have portfolio optimization. In the energy world, there is energy consumption optimization, and in different industries, there is we try to find the best way to allocate workforce or labor. So this is a slide which shows why optimization can do something which we cannot do manually or using any computer program. So so in this example, there's a warehouse. From the warehouse, I need to send goods to 3 different cities, A, B, and C, and the numbers you see on the arcs represent the distance between each of these combinations. So for example, 60 is the distance between the warehouse and city A, 80 is the distance between city A and city B, and so on. So since there are only 3 cities, there could be factorial 3, that is 6 possible combinations, which I've enlisted in the table below, and you can easily add up the distances of all these combinations, and using a simple program you can find out which one is the least distance. So if it is 6, it's very easy. But when you increase slightly from even 3 cities to 10 cities, there could be factorial 10, that is 3.6 million possible routes. And even with today's super fast computers, which can calculate the distance of a route in maybe a few milliseconds, it might take hours to find the hours or days to find out the best possible route. But using optimization, it becomes much easier and much simpler to find out the best possible route. And if you increase that 10 to 13 or 20, it becomes impossible even in days or years to find out the best route. So that's why optimization will give you a solution which is much better, and it will give you the solution faster. So these are some examples of how organizations have used optimization historically to achieve their goal of increasing their revenue or profit, or decreasing their capital expenditure. So as you can see, so one beauty of optimization operations research is that it can be used across any possible industry that you can think of. So if you see in this table, optimization, you can see the names of companies spanning across all industries. So you have airlines companies, you have semiconductor companies, and then you have banks and so on. And if you look at the numbers on the last column, these numbers will tell you how much savings or revenue increase was brought about by applying optimization in these organizations. So let's look at one problem from this slide, which is crew rescheduling. Which is crew rescheduling for continental airlines. So in airlines industry, optimization is used very massively, because so one application is in aircraft, in allocating aircrafts to different flights. So there are different an airlines will have different aircrafts, and they need to allocate these aircrafts to different flights in such a way that using those limited aircrafts, you can serve all the flights. So for example, there could be a flight from which starts from Delhi to Mumbai, Mumbai to Bangalore, Bangalore to Chennai, and Chennai to Kolkata. So at the end of the day, the aircraft ideally needs to return to the base location, which is Delhi in this case, because otherwise, if it lands in some other city, at the end of the day, then the airlines needs to provide accommodation and travel expenditure to the aircraft crew, which is expensive. So there are many constraints. I just gave you one constraint. There could be many constraints around that. So adhering to all those constraints, the airlines needs to allocate aircraft to the different flights. So another expansion of this is crew rescheduling, which I've shown in this slide. So whenever flights get cancelled, it could be due to multiple reasons, like unfavorable weather conditions, pilots on leave, and so on. The airlines needs to ensure that the passengers who are on the cancelled flight would get accommodated to some other flight. So either they would get accommodated, or if the passenger is not willing to move on to another flight, then they will get a refund. So the airlines will try to accommodate maximum passengers in the next flight as early as possible. And obviously they cannot allocate a new aircraft just for accommodating those the passengers of the cancelled flight, because that would be too expensive. uh, so they would need to accommodate them in the next available flights in such a way that the inconvenience cost to passengers is minimized, and at the same time the airline's cost does not increase too much. And there are multiple priorities or business rules, business restrictions which need to be followed. For example, senior citizens or people with infants, they need to be accommodated on an earlier flight or on the same day, and so on. So all these rules need to be followed, and then the allocation needs to be done, and this needs to be done very quickly, because once the passenger gets to know that their flight is cancelled, they cannot wait for a long time to get onto the next flight. The airlines needs to make the decision quickly. So this is called crew rescheduling model in the industry, and this is used by all major airlines today. And Continental Airlines was one of the first airlines to implement this model around 20 or 25 years back, and they were able to save $40 million in that year alone by applying this model. And after the 9/11 terrorist attack, Continental was the first airlines to resume normal operations. Okay, any questions so far? Okay, so in an optimization application, the major thing which the business looks at is how much monetary savings it is being able to bring. So whether, even if you are calculating the benefit by using some other metric, like for example in a vehicle routing problem. So vehicle routing is another area where optimization is massively used. So uh, for example, if you're talking about Amazon might have let's say 10,000 deliveries to make in let's say Bangalore in a day, and they have let's say 100 delivery executives. So how would it allocate those 100 delivery executives to the delivery, so that they can so that they can complete all the deliveries with minimum cost, that is by traveling minimum kilometers. And at the same time, we need to ensure that all those 10,000 deliveries happen within a day. So that is another area where optimization is used. And vehicle routing is today used. So this is commonly called as vehicle routing problem in the industry, and it is used by all e-commerce companies, logistics companies, all the food delivery companies like Swiggy, Zomato, and all the big logistics firms of the world like FedEx and UPS. So even for vehicle routing problem, we might be calculating the savings in terms of reduction of miles. But finally, when we convey the savings to the business, we need to calculate that in dollar terms. This is what is shown in the slide. So if by applying optimization, you're able to reduce the miles by 100. So let's say by following the manual process, your vehicles are traveling 1,000 miles in a day, and using optimization, it reduces to 900. So you are saving 100 miles in a day. So you need to look at the dollar cost per mile and calculate what would be the annual cost savings. Similarly, for a factory, if by applying optimization you're able to produce 5,000 units more per month, and let's say that each unit costs $100, then you could be potentially increasing the revenue of the company by $6 million. So this is how we calculate the monetary savings or monetary benefit of OR models. And apart from monetary benefits, there could be other benefits, other ancillary benefits, for example, automation, digitization, or reducing or eliminating manual process. So a person who was doing it manually on Excel might be requiring 1 day for the exercise, while using a model you could be doing it in 30 minutes. So that person is saving 7.5 hours per day, and that time could be used productively somewhere else. And there is also some cost associated with the optimization project. So whenever there is a person working, there's a resource cost, and also there are different very expensive solvers which are required for optimization. We'll come to that in a later slide. So that also has a cost. So that is how we do the cost benefit analysis. So in this slide, we look at some examples where optimization is helping the world in achieving its sustainability goals. So in the last slide, we saw how optimization is helping a company to make more money or save more money. But apart from saving money or making money, optimization also helps in reducing carbon dioxide emission and other sustainability objectives. So these are some examples where different companies have used optimization, specifically vehicle routing problem, to reduce their carbon footprint. So for example, Walmart, by applying optimization model for their supply chain planning, they were able to reduce carbon dioxide reduction by 72 million pounds every year. And UPS, which is another big logistics company in US, they were able to cut down their CO2 emission by 100K tons every year. Apart from that, there are other very interesting applications. So we'll look at these. One is electricity distribution. So electricity distribution is a very interesting problem because electricity, unlike other commodities, cannot be stored. So once electricity is produced, you need to either consume it, or if there is not enough demand of electricity, then you need to dump it down the ground. So the electricity, as you know, electricity production, as you know, requires natural resources. So whenever we are producing electricity, we should not be producing so less that there is not sufficient power, and which leading to power blackouts. And at the same time, you should not be producing so much that you are not able to consume and you need to waste it. So electricity, that is another area where optimization is used. And then agriculture. So as the global population is increasing and the land available for agriculture is reducing, we need to ensure that on the limited land that we have, we can produce maximum crops. And in the Western countries, optimization is very scientific, and optimization, math, science are very much used. Technology are very much used to ensure maximum output from the land. So the main objective here is maximizing the production on the land that you have, and there are multiple constraints. For example, different crops require different require different time periods to grow. Some crops can grow in 3 months, some crops can grow in 6 months, and then there are different seasons for growth, for better growth. Some crops can grow throughout the year, some crops can grow only in a particular season of the year, and then some crops grow better if they are alternated with another crop, and so on. So there are multiple constraints which are adhered to, and after following those constraints, the model tries to ensure that the model suggests what is the best way to best plan to uh, schedule my crop production so that the net output from the land is maximized. The other area is in healthcare. So in healthcare, so for example, the first one I'll skip. I'll move to the second one. So facility location problem is another area where optimization is used. So let me give you a simple example. So let's say, for example, if Reliance Fresh wants to open two more stores in, let's say, New Delhi, and it needs to decide where it can set up the store, in which part of the city, so that it can get maximum sales, and at the same time the real estate cost is not too high. So um, and so basically the demand is met and at the minimum cost. So United Nations has these warehouses globally where different emergency kits are kept, so that whenever there is a natural disaster anywhere in the world, it can send the relief material as fast as possible and with the lowest cost. So facility location model is used in solving such problems. Okay, so now we'll look at some we'll look at some types of optimization problems which are commonly used in the industry. So most basic classification of optimization is classical mathematical programming, which would have an objective function and constraints. And constraint programming, in constraint programming, there is no objective function, there would only be constraints. And constraint programming is typically applied for scheduling problems in factories where there are some very complicated constraints which are difficult to model using classical mathematical programming. And the next classification is based on the type of input data. So if the input data is known with certainty, then it is deterministic programming. And if it is not known with certainty, then it is stochastic programming. And the next classification is based on the type of variables. If all the variables are real, then it is linear programming. If some of the variables can take integer values, then it is integer programming. So for example, if I'm talking about an automobile plant, then you cannot produce, let's say, 3.7 cars, right? So you can produce either 3 cars or 4 cars. So we need integer variables for that type of problem. And another subtype of integer programming is binary programming, where some of the variables can take binary values, that is 0 or 1. So for example, if you have in a factory, let's say you have 100 machines, and you don't want to run all the machines on a particular day, because if there is not that much demand, then you don't want to run all the machines, because the machines would have some operational cost of just for running. So you want to minimize the number of costs. So the decision as to whether the machine should run or not on that day, that is switch. There is an on-off decision. So for that, we need binary variables. And apart from that, there is also nonlinear programming when either the objective function or constraints or both of them are nonlinear in nature. So the simplest type of nonlinear programming could be when the variables are quadratic in nature. But so in industry, we generally try to avoid nonlinear programming because of one is not too many solvers are capable to solve nonlinear programming problems. Secondly, nonlinear programming problems, it is difficult to assess whether or understand whether you have arrived at a global optima or you are stuck at the local optima. And it is because of all these mathematical complexities we generally try to avoid in industry. So in industry, we generally have linear programming, not even linear programming, we generally have mixed integer programming or constraint programming problems. Especially in manufacturing industry, there are a lot of constraint programming problems. Okay, any questions so far? Okay, so how is the difficulty level of an optimization problem defined? So we look at number of variables, number of constraints, and we decide, and also some other factors like what solver we are using, what is what is the formulation. So the formulation could be a strong formulation or a weak formulation. Sometimes if it's a weak formulation, it could lead to more solve time. And stopping criteria. So generally what happens is in integer programming problems a problem with even a few integer variables can sometimes take a lot of time to solve, even days to solve. And there is also a large amount of memory consumption. So in the real world, we cannot sometimes we cannot allow the model to take a long time to solve because we need to tell the solution to the customer. So we apply a rule that let the model, we can apply rules, for example, like stopping the model after 10 minutes of running, or stopping the model after we have achieved let's say 90% optimality gap. So how it happens is, as you move closer to the optimal solution, the runtime does not increase linearly, the runtime increases exponentially. So you might get a 90% optimal solution in 5 minutes, but it might take another hour to get a 95% optimal solution. So these are some of the factors which determine how difficult an optimization problem is. Difference between, okay, I'll skip this probably. Okay, so these are some areas where optimization is used in manufacturing. The first example is, we call it economic order quantity, or when to order, how much to order, and what to order. So if you have ordered too much, then and you do not have that much demand, then there are multiple disadvantages. One is you have purchased from your supplier or vendor, so you have your money unnecessarily being held up. And the second point is, if your inventory is perishable, then there is a chance that the inventory might get spoiled in the time you're keeping it in the warehouse. And the third is, there is a maintenance cost of storing it in your warehouse. So, and at the same time, on the other hand, when if you are buying less than what is required, then your demand is much higher than what you have purchased, then you may not be able to fulfill all the demand, and that leads to loss of revenue. I'll skip this. And the other example is in production planning. So in the factory, in the factory shop floor, there could be multiple constraints around machines, around people and time. So there could be limited machines, there could be limited manpower available, and there is of course only 24 hours in a day. So within all those constraints, within all those boundaries, you need to ensure that your production is maximized. And there could be a lot of other operational constraints, for example, changeover, and so on. So how do I maximize the production with all those constraints? And the third major aspect is, once I have produced my material in the factories, I need to ship it to my end customers, or to my warehouses, or to my retail stores. So how do I do the routing or the shipping? So for example, should I be using one big truck, or should I be using two smaller trucks? Because one big truck might be cheaper than two smaller trucks, and so on. And there are and the constraints that need to be respected here are achieving this transportation with minimum cost, and ensuring that the goods reach the customer or the end user before they require it. Okay, this one I'll skip. Okay, now airlines is another area where optimization is used. So as you know that as we move closer to the flight departure date, the price in general keeps increasing. So in this example, there are three flights of an airlines at 5 p.m., 7 p.m., and 9 p.m. both for the same destination. And as you can see, for the 5 p.m. and 7 p.m. flights, the passenger fill rate is relatively higher, so around 75% seats are sold. But in the 9 p.m. flight, almost half of the seats are unsold. So how does the airlines ensure maximum revenue from this seat? One is it can offer discount. Now the decision which needs to be taken here is, one is first of all, if you're offering a discount, then how much discount should you offer? Should it be 10%, 20%, or 30%? And the second point is, at what point should I start offering the discount? Should it be just 2 weeks before the departure date? Should it be through 3 weeks before the departure date, and so on? So this is a very complicated problem, which is a combination of both machine learning and optimization, because multiple factors need to be looked at here. One is at the time of the flight. So for example, if it is Diwali, then I know that even if 40% of my seats are unsold, still they will all get sold out in the last 2 weeks. And what is the price the other my competitor airlines is offering, and how many days are left for departure of the flight, and what is the demand, and so on. So based on all these factors, I need to ensure how much discount to offer in which flight. The same example, this is an extension. So as you can see, as we move from left to right, as we move closer to the flight departure date, the price in general keeps increasing. But around 1 month before the departure, we might have observed that a lot of seats are still unsold in a particular flight. So the airlines decides to reduce the price from $600 to $450. So this is again an example of dynamic pricing based on the available inventory and the time to departure. During COVID, also optimization was heavily used, especially in big countries like US, where allocation or distribution of vaccines was a very complicated and challenging problem. So the objective here was to ensure that the vaccines reach the people fastest. But again, there were multiple constraints which had to be respected here. For example, um, the priorities groups, for example, senior citizens and people with comorbidities, they had to be delivered the vaccines fastest. And then some vaccines had dosage requirements. Some had 2 doses, some had 1 dose, and then there was a gap interval. So if you're there's a gap of let's say 2 or 3 months between certain vaccines. So those regulations had to be respected, and respecting those, how do you ensure that the vaccines reach the people in the most effective manner? They're distributed in the most effective manner. And similarly, for the other medical equipment like PPE, ventilators, ICU beds, medical personnel, also optimization was used to achieve the best possible distribution. Okay, so these are some solvers, commercial solvers, which are commonly used in the industry. So in the industry, the problem sizes are very large, and you cannot solve these problems using open source solvers, because open source solvers will have a certain size limitation. And so the gold standard in optimizations is IBM. The name of the software solver is called Cplex, which was originally owned by a company called iLog, and then it was purchased by IBM in 2008. So this is the gold standard and most massively used solver globally. And this is again very expensive. Each license of this solver costs around $60K. The next most popular solver globally is Groby. This is much cheaper and costs around $15K. And the other major solvers, commercial solvers, are FICO Express and SAS OR. And as I said, open source solvers have some limitations in terms of problem size. So how are optimization solvers connected to API? So these solvers, which we spoke of in the last slide, we can directly write in their own language, but you can also write in any standard programming language and call these solvers independently. So for example, you can write your mathematical model in Python, C++, C Sharp, or Java, and then you can call the solver from invoke the solver from any of these languages. So in the programming language, you write the model, and then the mathematical model is just the mathematical model which is passed to the solver, and then the solver will solve the problem and give you back the output in a raw format, and then the output can be processed in any format that you desire. And for example, you might just need an Excel output, or you might want to output the solver result to a database, so you can do any of that. Okay, so basically these are the steps in optimization project for in terms of OR. The first step is requirement understanding. So we understand what is the requirement from the business, and then we design the mathematical model, and then we do the mathematical programming. And after the programming, we do the testing. So it could be testing the objective function, testing the constraints, ensuring the performance is good. That is, we are able to solve the model in reasonable time. And after that, we let the users test the model. And after the users have completed testing the model is put to production, and it is deployed and put to production. And even after deployment, there could be some other requests from the users in terms of post-production support, adding more functionalities, or there could be some bugs which need to be fixed. So this is how the typical solution architecture looks like in OR projects. So there would be a user interface. In general, there's a user interface. There would be database. So for the user interface, we would pick up the data from the database, and there would be the optimization solver. In this case, we have used Express. I've shown Express and Python as a programming language, but it could be Cplex or anything else. And the optimization code would then get triggered from the UI, and once optimization runs, it would push the results back to the database. I mean, we can write some code in the at the end of the code to post the results in the database. These are some factors we need to look at when starting an optimization project. What is the planning horizon? That is for how many months or weeks or hours you want to plan. So if it is a very operational problem, then you could be planning just for the next shift or for the next day. If it is a very strategic problem, then you could be planning for the next quarter. So you might want to decide how much raw material I want to order in the next quarter, or in the facility location problem, you might be wanting to decide where to open my next next warehouse in the next in the current year. So that kind of decisions do not need to be taken very often. So you might be planning for the entire year. And then how frequently you want to run the model, whether you want to run it every hour or every day or every 30 minutes or so on, and what solver you want to use based on how much budget you have and what is your requirement. If it is a very straightforward and simple requirement, you could probably be using a open source solver. If it is more complicated and the problem is big in size and you need the model to be integrated with other applications, then probably it's best to use a commercial solver. Who would be the users of my model, and what would the implementation details around the UI database and so on, and how much time you need the model to be solved. So if the model needs to be solved very quickly, then you need to model it in a different way. But if you are okay with letting the models take a few hours to solve, then you could be following a different approach. And what are some of the hard or soft constraints? So hard constraints are essentially those which must be adhered to, and soft constraints are those which are good to have but not essential. So we need to clarify with the user which constraints are hard and which are soft. I will skip this rest of time. So these are some challenges. Okay, so I'll quickly go through what are some of the career opportunities in OR. So in OR as a career is pursued mainly by people from engineering or quantitative sciences background. So I've seen a lot of people from mechanical engineering background who go for a career in OR, because OR is used very massively in manufacturing companies. So mechanical engineering, chemical engineering, computer science, industrial engineering. So these are some of the common engineering fields from where students pursue higher studies in operations research. So IEOR is nothing but industrial engineering and operations research. And people from quantitative sciences background like maths or statistics also sometimes go for a career in OR. And after completing their higher studies, people can join either academia or industry. So in industry, there could be product companies, service or consultancy firms, or core analytics firms, which work in OR. Why you should take up an OR job? Because it is very intellectually challenging. The nature of work is non-repetitive, and it is extremely specialized and niche skill, and hence it's high paying. And you can work, OR is not restricted to any one particular domain or industry. It spans across all industries, so you can work in whichever industry is of your choice. So some people some people prefer to stay in the same industry. Some people prefer switching across industries, and some people have a particular preference, like some people want to work only in airlines, or only want to work in manufacturing, or only logistics. So it's up to you. And it's the nature of work is very innovative in nature. And what are some of the skills that are required for pursuing OR as a career path? The most basic skill that is required is math oriented skills. So you need to understand different OR models and techniques, and you need to know all the techniques and techniques, so that whenever there's a problem that you are put onto, you need to understand or identify what technique should be best applied. So should I apply constraint programming? Should I apply integer programming? Or what should be the type of formulation? So formulation is another important skill. So you should be able to formulate the problem, formulate the objective function, constraints. And even after having built the model, we need to sometimes dig into issues of infeasibility, explainability, etc. It's good if you have experience in at least one solver. Among the programming skills, it's programming skills also very required, because you need to write the, after having designed the mathematical model, you need to write the mathematical model on code, in the code. So you should be proficient in at least one programming language. It could be any of the standard programming languages, and it's good if you have some database knowledge. And domain knowledge is another area. So if you are working, again, that will not come in the first come before you join organizations. After you join an organization, you should gradually develop knowledge about that domain, because unless you understand the business, it is very difficult to apply a mathematical model. And apart from that, you should also have some soft skills, because OR problems are very open-ended and ambiguous, sometimes very ambiguous in nature, because the person who has given you the problem, they may not have sufficient idea about the problem themselves. So you need to understand what is the right problem, and what is the problem. You need to define the problem scope, understand what is the right problem that you want to solve, and then you should tell the stakeholder that this is the problem that I would be solving, and this is the expected model outcome. And after having solved the model, we need to ensure that you are explaining the output in business language and not in mathematical language to the client, and also presentation skills. So yeah, that's what I had for today. Let me know if any of you have any questions, or you want me to elaborate more on something.
Okay, so I have some. I think there are some questions in the chat.
Sure.
Can you see the chat?
Yeah, 1 second. I can see the chat.
There is a question by Motiranjan Gupta which I answered. His question mainly was why is there so much hype on optimization when most of the optimization problems, as you are discussing, are linear in nature. So my answer is that there are convex nonlinear optimization problems that people solve all the time. Right. Basically, his question was from the point of view of, neural network based solvers or machine learning, So if you want to add something more, please go ahead.
Yeah, sure. So one thing I would point here is OR is quite different from machine learning. So in OR, there would be an objective function on and constraints. And the reason why, every problem would have not the reason, the point is that every problem would have a different approach, because in the real world, but sometimes when you go through literature, when papers go through papers available in the literature, you will see, you might feel that, okay, this problem is similar to another paper. But in the real world, every organization would have a different problem, and you cannot apply the same model in all organizations. So there are a lot of companies, for example, in supply chain, there is a software called Supply Chain Guru, which can solve optimization problems, but that again is not very, it is used by many organizations, true, but it is not very popular, because different companies have different problems. So you cannot apply the same standalone model to all organizations. That is point one. And even for the same organization, their problem, their dynamics might change very frequently. So in my example, in my experience, a couple of years back, I solved a problem using MIP formulation, and after the model was built, then suddenly the user told that, this there is this additional constraint which I forgot to tell you before. So after they told this constraint, we had to change the entire formulation, because that could not be solved by a by MIP formulation. So we had to go for a constraint programming formulation. So in the industry, it is very dynamic in nature. So, and these days there are a lot of questions about automation and Gen AI and all. So in optimization, you cannot apply any automation, or you cannot apply any tool to just tell your requirements and it will give you the model. No, that is not possible. So it needs human insight. Hope that answers your question.
Yeah. So there is another question from Aditya Chalna. Is that given all the good solvers for optimization these days, the main bottleneck is possibly to convert a business problem into an optimization problem, which should be solved. Can you shed some light? On some generic guidelines which one can use for this?
Yeah, so actually this is, I would say, this business problem to optimization problem conversion is tougher than the optimization problem itself, because and there is no generic, there are some generic guidelines, of course. So I don't think I have in another slide, probably I'll share that later. But the generic guidelines are one is, but even after following all those generic guidelines, later the client can say that, this constraint I forgot, or this is not what I intended to mean. So one is, first of all, you should not build the complete model. So after having understood the business, or at least after you thought that you have understood the entire problem, you should not build the complete model and then tell the user that this is the model, is the output, because then there are a lot of chances that you have spent a lot of time building the whole model and then you have missed something, or misdid something, right? So you should build it in steps. So you should first start with the most basic constraints, most basic objectives, and then you should show the output that this is I considered only and you should assume all the other things. You should make a lot of assumptions initially, and then with those assumptions and with those basic constraints, you should share the results with the user, the stakeholder, and then get his or her green signal, and only then go to the more complex or more the other constraints. So you should take it, you should follow the agile methodology, like you should follow one step at a time. Don't do everything together. So that is one thing. And then you should be very clear with the user about what they want, and that should be documented somewhere, so that later on the user cannot, or the stakeholder cannot say that, no, I meant something different. It should be documented. And the other issue is, I've seen that even there could be multiple users or stakeholders, right? And even among the stakeholders, within the same organization, different stakeholders might have different things in their mind. So one stakeholder might be saying that, okay, I want objective 1, for me objective X is most important. Another stakeholder might be saying objective Y is more important, and so on. So so there should be proper alignment among the stakeholders before you start working on the model. And
please.
Yeah, and the other thing is, after you have built the model, the first thing the user will do is they will compare their results, that is what they're getting manually, with what you have. So obviously what you are getting using optimization should be better than what they are getting manually, or using whatever program or whatever you're doing in Excel. But sometimes that doesn't happen. That could be because your model is wrong, but generally it is not because your model is wrong, but because you might have considered you might or might not have considered some constraint which they have considered. That could be the reason, or there could be some difference in input data. So those things need to be checked.
Okay, so I have some points here. So one, my thought about the question that Aditya asked is that if someone is expecting that the business problem which is expressed in maybe formal or semi-formal language, translating that into a set of variables and then the objective functions, etc. That there is, I don't see any guideline per se. I mean, it's not that. I mean, maybe for a particular domain, based on experiences, people might say that. Otherwise, in general, having guidelines or having a kind of prescriptive method to translate a business problem to mathematical formation is almost impossible, I think. I have a different point here. So I mean, I'm not an optimization person at all. I don't understand this that well. But in my past this thing organization where I was asked to look at a product which actually had a solver, and that product was supposed to and that product was deployed in oil and gas domain, specifically for those gasoline content analysis and fuel mixing there. So apparently that solver was there for a long time, and typically in those kind of domains, the core solver part, once people actually fix it, it does not change very frequently. The overall thing remains the same, though the other paraphernalia changes. At least that's what I saw. But my question to you is that when I was called there, I was called because that whole they were migrating from one version to another, and then when they migrated and they kept the solver, the code part the same, but the overall solution that they are getting in the new version was very different from what they used to have in the earlier version. And so my question to you is that, do you have, from software engineering perspective, do you have any regression testing or any other testing guidelines for these kind of optimization problems? How do you test?
Yes. So yeah, so one is I'm not sure what you meant by version. So I think so sometimes the solvers have different version upgrades, and there's a lot of work going on in upgrading the making the solver's logic more better. So after changing the solver version, there could be a there would always be in general there would always be an improvement in the output, improvement in the sense improvement in the objective function. So what we do is after regression testing, meaning what we do is after, like, let's say there is version X and Y, so we make sure that Y and Y is a later version, so we make sure that the objective function of Y is always better than X. We run different scenarios we run different test cases, and one is that the objective function should be better. The second is that the runtime should be better in the sense better or at least equal to, and the runtime should be equal to or lesser than what was there in the previous version. So these are the main these are the two
I'm
main.
not talking about that. I'm talking about the quality of the result that changed. Like for certain inputs, the output was similar to the previous version. Well, I'm using the version. I don't mean that the version of the solver changed that much, but essentially they migrated from one platform to another. Okay, with I mean, in any of these products, the maybe the 80% is basically the software, and then only 20% is the core solver part, as in even in AI. But what happened? I mean, so they were grappling with this, that while other parts have been tested well, but as this solution progresses for certain inputs, it's good. But then again, as they keep changing inputs, or maybe as they run it for a long time, gradually there is a deviation from the older one. And at least they were struggling for months to basically find out what is going wrong. So I just try asking you that in general, this kind of scenarios can happen, and is there any industrial kind of good practices, best practices, or do you not face this at all?
No, I've never done a platform conversion, but yeah, before doing the conversion from moving from one software version to another, you should always check if you don't know what will be the input in future, but at least for the current inputs, you should be testing for at least maybe 15 days. Whether you're getting similar or better output in the newer version, newer platform. But yeah, if the input is the same, then and the solver version is the same, then you should not be getting different outputs on different with software upgrade. Let's say you're moving from Java to Python or whatever, you should not be getting that unless there is they change something else. Maybe they change the runtime, or I don't know, something like that. Yeah, but sometimes we feel that okay, with a newer set of outputs for which you have not tested in the old version, you feel that the output is bad, but unless you test it on the older version, you cannot say that with certainty. Did that answer your question?
Yeah.
Is there any other question? Not. We thank Mr. Giri. It was a lovely talk. Actually brings back memories of linear and nonlinear optimization that I used to do from the same point of view that you are practicing right now, like probably more than a decade back. I don't do that kind of optimization anymore, but thank you very much for the talk. And it was lovely to meet you finally. And we hope that you would be able to spare some time and visit us on campus in Goa in future.
Sure. Thank you so much. Yeah. Thanks for inviting me. Thank you, everyone.
Thank you.
Bye-bye.